Hello, everyone. This is Professor Ma, and this is the introduction of the sections on double integral over polar coordinates. More precisely, we're going to talk about double integral over a domain that's defined or enclosed by polar equations. And in fact, this setup in three-dimensional space function over a polar plane, we call these coordinate systems the cylindrical systems. So in particular, we'll be looking at functions defined over a region that's defined in the following manner. That is, it's trapped between two polar curves, R1 theta, R2 theta, but between at some angle theta between some angle A and B. Okay. And how do we, first of all, what's the relationship between the area if we cut the in the variable dr d theta? That is, if suppose we take the plane, we cut the whole plane into very small concentric circles of dr, and then we cut the theta into partition into d theta, so in the slivers of angles. And the question then we want to ask is a typical uh, chunk, if you want to say, a piece of area like that, which we call delta A. How big is it in terms of dr, d theta? And then the answer from last sections before, we see that the area, the delta A, is approximately equal to R, over here R star, which is some points, any points just inside the shapes, the distance to the shape times the dr and d theta. So we have this differential relationship telling us how approximately how large this piece is. So this is approximately area is r times dr d theta. Okay. So suppose we have a function now defined over the polar plane, the xy plane in polar coordinates, and that I want to calculate the volume of the underneath surface. Okay, so what we do, we partitions the domains into dr d theta, and in particular, let's calculate the volume that sits over one of these little pieces. Okay. Well, the area of the base for this little piece is approximately that. Okay, from we have the dA, the differential of the small area in terms of dr theta, and then the height of the column is approximately this, where R star theta star will be some points inside here. We calculate approximately how high it is. And then this gives us the approximate volume of that particular column. That I want to add up, of course, this is the partitions over the domain. So I have to calculate the column that sits over every one of these little pieces. And I want to calculate the columns and add up the volumes of all the columns. So in formula, it looks like that. And then I want to let the theta, d theta go to 0, then the radius of dr go to 0, becomes smaller and smaller, thinner and thinner, and more finer and finer column in the calculations. And remember, this part is the base area, dA, times the height of the column, z, and that gives the volume. So, and that's integral of these of the function over the the area differential. Okay, but remember this area differential we can change it into polar coordinate RD theta. So in terms of RD theta, so this is the conversions of how to calculate the volume sits underneath equations of this form. Incidentally, equations like this is really a cylindrical equation. Okay, so let's just go about a cylindrical coordinate. The cylindrical coordinates basically is defined in the xy plane, defined by the polar coordinates, but then you tack on in the third dimension, the z, you just tack it on as a third component. So they are defined as r theta z. So we can easily convert the first two numbers into a point on the xy plane, that's the polar coordinate, then you look at the last number z to move the points up and down in the z direction. Okay, so that's point 3 120 degree 4. Okay, or 3 2 pi or 2/3 pi 4. Okay, right? And I can calculate the coordinates using the conversion rules in polar coordinates. Okay, and this is how, and then part of this is how do you put a point in rectangular coordinates into polar coordinates, okay, into the cylindrical coordinates. Okay, and then we can define equations in these coordinate systems. So the equation r is equal to a constant, and on the polar planes, circle in cylindrical coordinate z can be anything. Therefore, the circle on the plane becomes the cylinders. And similarly, the equation for a line going through the origin defined by the angle in the cylindrical coordinate is an entire plane that's sits over in the angles in direction of the given angle. Over here, theta equals 3 pi over 4. It's this entire panel that sits over with the angle 3 pi over 4 thetas. And from these, we can actually get some quite interesting surface. So here are a couple of them. Okay, here's the equation. Z is equal to sine r. There's no theta here, and this is what it looks like. Okay, in particular, to see why it does look like that is notice when theta is equal to 0. Okay. Sorry. What I'm going to say. When r goes from 0 to pi, the z rises. Okay. Let's fix theta equal to 0 first. Okay. So when theta equal to 0, then when r goes from 0 to pi, sine of r goes from 0 to 1. Okay, back to 0, pi over 2, back to sine of r goes to 1, then back to 0. So here's pi over 2. So therefore, the curve is theta equal to 0. And in particular, I can now let theta be any angle. So therefore, I get these cross sections of all the same curve. I get these cross sections. So it's like, therefore, you take that curve, will rotate around 2 pi, like a blanket, and that's the surface. Okay, and here is the surface, is a different surface. Okay. If I multiply sine of r times the angle theta, then in particular, when theta is 0, then I don't get this curve anymore. And when theta is equal to 0, actually I will get 0. Okay. As the angle theta increase, so this is as theta equal to 0. As theta increases, let's say theta equal to pi over 4, then I plug in pi over 4 times sine of r. Again, for r between 0 and pi, the sine of r takes some value from 0 to 1 back to 0. So it makes these little kind of like a little sine curve. Then as theta increases, gets bigger and bigger, the angle gets bigger and bigger, then these sine curve gets higher and higher until when theta becomes 2 pi, then the curve is this one in particular. It hits the high point at pi over 2 pi, 2 pi. Okay. So that's the shape for this one. So the interesting part about these examples is actually the graph itself. The calculation is pretty easy. The calculation to calculate the volume underneath this surface, we just convert them into polar coordinates. Okay? And the domain they sit on is the disk of radius r. I mean, radius of pi. And the first integral I can change into this domain r dr d theta, so it's going to be sine of r integrated over this double integral, and you stick your sine of r into, that's what f of r theta is right here. And so the first volume is that, and the second volume is this one theta. Okay. And these are straightforward calculations, pretty easy, so you can find the answer for that. Here's another one, which is slightly harder to see. F of theta is cosine theta. Okay. And we want to talk about the functions over the domain. In particular domain is as I is between 0 to sine theta and theta between 0 and pi over 2. In particular is that we want the domain to be this half circle, right? Okay. And what does a function look like? The function looks like this. Okay. When theta is equal to 0, z is equal to 1. Okay. So therefore, an r can be any number. So therefore, when theta is equal to 0, I get all the points. I get every point along this line. As such, 1 unit above the x-axis. As the theta, this is along theta equal to 0. Along theta equal to pi, say pi over 4. Theta equal to pi over 4, say, or pi over 6. Let's say theta equal to sine of pi, no, pi over 3. let's say we choose the angle pi over 3, theta equal to pi over 3. If theta is pi over 3, r is equal to cosine of theta of pi over 3 is 1/2. Therefore, the z is 1/2. I get these points. But actually, I get these points along on the surface along where r can be any numbers. Okay, so in other words, this particular surface formed by taking the line and make it a twist. And if I turn this, look at it sideways, I want to calculate the volume of this, like a drape, like a sheet that I want to calculate that volumes that sits over the semicircles that cover under the sheet. So that's a volume we calculate. And the setup is pretty easy. The conversion is pretty easy and the straightforward calculations. Okay. Here is a problem that we translate the a regular rectangular coordinate double integral using change of variables, because this area, the domain of integrations, if I take a look at this boundary of integrations, it says x is between -2 and 2, and for y travels from -√4 minus x squared to 4 positive minus squared. And this, of course, is the circle. So, in other words, we are integrating over the area of circles of radius 2. And these equations is x squared plus y squared. And of course, we can translate that into polar integration, because that's given, that's just the in polar equation, that's just given by equation r is equal to 2. And then theta go from 0 to 2 pi. So therefore, I can change this into theta go from 0 to 2 pi. R go from 0 to 2. And this, of courd, is r squared, x squared plus y squared, to the 3/2 power. And dA, this become r dr d theta. Okay. So that's the reformulations. And then the rest you can calculate it. It's pretty straightforward. So that's it. That's how we convert things to do double integral over region defined by polar equation. And how do we change the equations and change the limits of integration into r and theta. Okay. Bye-bye. Bye-bye.